Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. Forecasting road traffic is a long-established problem that many machine learning approaches have been applied to. It's no surprise that deep learning, a popular modern technique, would also be applied to this problem and, of course, work with some success. Seems like maybe we require deep learning for computer vision, but do we really need it for road traffic forecasting? That's the question posed by today's guest, Eric Manibardo and co-authors. We talk about their study and the benchmarks they established to try and answer this question.
Hello everyone, my name is Eric Manibardo. I'm a PhD student at the University of the Basque Country in the north of Spain. I also work with Tecnalia Research and Innovation, which is an engineering enterprise, private enterprise.
Well, tell me about the focus of your PhD. What are you researching?
My PhD is mainly focused on trying to extract some findings in the context of pedestrian and also vehicle mobility in what is called Intelligent Transportation Systems research line. I'm mainly focused on predicting traffic behavior, predicting traffic congestion, every kind of traffic state, also accidents, by using machine learning techniques.
And can we talk a little bit about maybe traffic congestion forecasting? I think we all understand what traffic congestion is. We've probably been in it. But what exactly do you want to predict? Like, is it the congestion 5 minutes out, tomorrow? What's your goal?
It is not only my goal, but it is the goal of mainly the government, because every time a congestion state occurs, the population is losing a lot of money in the context of gas oil, in the context of loss of energy, in the context of loss of time. So everyone is trying to avoid the congestion state. What are we trying to predict? We are trying to predict when congestion is going to occur, so we can tell people not to go to some streets at certain time stamps to alleviate that congestion.
And what's the data set available? How do you measure congestion?
Okay, there are mainly two types of data. You can gather with roadside sensors. That can be a type of inductive loop, and wherever a vehicle passes, because it is metallic, the inductive loop is going to count +1. And you can also measure it with radar sensors. And other kind of traffic data is called floating car data, and it is collected from the GPS signals. And if you are in the building, also from the Wi-Fi signal, but mainly from GPS. With that, you can extract the trips and the journeys of different vehicles like taxi and buses. And from that kind of data sets is where we extract our conclusions.
Do you have to deal with noise or imprecision in those two forms of measurement?
Yeah, definitely. What kind of anomalies are we encountering? A lot of times there are outliers in the form of misleading aggregations, because at the road you often or usually have multiple lanes. So if you don't collect the information well, you can sometimes have 3+ times the normal car activity, and that's an outlier. It's because you have count 3 times the same number. Other times you have missing data. The traditional missing data, for example, few days there are some modifications on the road and the sensor is turned off, so you cannot collect data. Well, other kinds of common noise, but we don't, at least in my department, we are with our team, we don't want to smooth too much the signal, because you also lose quality information.
So I definitely see how that signal could be useful in making future predictions. You have a nice time series of historical measurements of, I guess, the rate at which cars are passing through, but that alone can't tell the full story. The solenoid doesn't know if it's a holiday, for example, or if there's a sporting event. Are there any other features that you pull into the work to supplement that in any way?
Yeah, of course, but here let me puntualize that there are two types of forecasting, the short term and the long term. In the short term, you are only trying to foresee the close future. So it doesn't matter too much the weather or the area where you are trying to forecast. The information that mostly matters is what have already been passed in that target location. So for that kind of task, I would say that the most important thing is the current time series, the current flow values, speed values. But for long-term forecasting, when you are trying to foresee a month in the future, a year in the future, what are you trying to see is the traffic patterns. Here, it is indeed important to see the weather, to see if there is a match event, baseball event, or whatever kind of important event, if it is a holiday, if it is a normal work day, or if it's a Saturday, a Sunday. So it depends on the task.
Well, the short term is interesting. So if the local time series is strongly predictive, that might be all I need. Can you talk a little bit about the methodology? You'd mentioned using machine learning. How does one go about making a forecast at a short-term time series of traffic congestion data?
The simplest way to predict traffic forecasting is when you have accessible data at the target location where you want to predict. And then if you have, I would say it depends the task, but I would say that the past hour of recordings, you can make a good proper predict for the next 15 minutes or 13 minutes for the short term. And how? Well, what I would do is to make a kind of vector with the traffic metrics. In this case, it can be speed or the flow, the number of vehicles that have passed for a certain timestamp. And that would be mainly the input for a random forest, for a SVM, or for another deep learning architecture.
Well, yeah, let's get into that choice then. The paper that I originally connected with you on is titled Deep Learning for Road Traffic Forecasting. Does it make a difference? So it's no surprise to me that people would be applying deep learning. Before we get into the big question of whether or not it makes a difference, can you talk a little bit about how deep learning gets rolled in? I mean, do we do any pre-processing of features, or do you just throw raw data in and hope for the best? What are the approaches, I guess?
For this task in traffic forecasting, usually you use the same pre-processing techniques for data, because what people in this field are not seeing, or maybe yes, but is that the traffic signal, it has a lot of valuable information. It is not like medical signal, for example, an electrocardiogram signal, where it is not that clear that it is a ventricular fibrillation or an asystolia. Here, if you see how many cars are passing or how the average speed of the road drops, you can tell without a deep knowledge if there is congestion or not. So with this idea in mind, you don't need to pre-process too much the data just to fit deep learning architecture.
So when you look at the raw data, you'd mentioned it's not obvious that there's congestion there. To the untrained eye, what does a visualization look like? What would I be visualizing if I tried to visualize the raw data you have?
It depends on the traffic metric. Mainly, the traffic data sets are in the form of flow, how many vehicles are passing, or in the average speed. So you measure the speed for all vehicles for a third time span, and then you compute the average speed. So for the first one, for the flow, what you would see are two main spikes. The first one in the morning when people is going to work, and the second one when people are returning home. These spikes can be narrow or wider depending on several factors such as the culture, the weather, the weekdays, holidays, and so on. And for the average road speed level, what you would see is that it stays still close to the average value of the road limit, and then a sudden drop occurs when congestion occurs, because if the lane is congested, you cannot drive so fast. So that's the two main visualizations.
And what is state-of-the-art, or what has been historically, when you go to try and predict this problem? Are there known techniques that have set standards, or is it still an open area of research?
So in the last 20 years, or at the beginning, I'd say, people began to use ARIMA. I don't know if you know what it is.
I do, but maybe a quick reminder for listeners would be good.
Okay, so an ARIMA, it is a kind of statistical modeling where you try to fit the time series behavior with statistical features. After that, what comes to the state of the art was the shallow machine learnings, the traditional random forest, the decision tree first, the SVM, the nearest neighbor, and then maybe 5 or 6 years ago, everything was deep learning. Why? Because it is my thought, at least, that if you put in your paper an exotic deep learning architecture, it is easier for the journal or for the conference to accept your paper. So it is like the winning horse.
That makes sense. It's certainly a good hypothesis. We know from the literature that, yes, deep learning is a very hot and trending topic, but that doesn't preclude it from being some step forward. We have seen things like translation models, for example, go leaps and bounds better when we apply deep learning. Perhaps they could for traffic systems as well. What standards should we use to look at it?
With this paper, what we wanted was to make people ask themselves the following. Why are we applying deep learning modeling techniques for short-term traffic forecasting? What we must first understand is that deep learning is a subset of the whole machine learning toolbox. And yes, I like to call it a toolbox because, at least for me, there are a set of modeling techniques that allow us, the data scientists, to understand, predict, and classify natural processes. And as a tool, deep learning is now simply an overall better tool, and therefore it should not be applied blindly for any task. This is the key point. Well, why deep learning? Because it has automatic feature learning, because it can model any kind of natural task if you keep adding layers to its architecture. And yes, this is true, but it is not necessary for short-term traffic forecasting because we are so close in the state of the art to the 100% accuracy. So there is no room for improvements with this technique. And if you are not improving the state of the art or the improvements are marginal, why are you choosing these kinds of techniques, the deep learning models, if they have so many disadvantages in the form of it is a black box, you cannot tell why it is deciding that tomorrow is going to be the congested traffic, whereas if you use random forest, you can follow its decision tree and see why it's predicting like that. Deep learning also consumes a lot of hardware resources that are not necessary, and deep learning also tend to overfit regarding shallow learning techniques, in the form that deep learning is tend more, at least, to learn the singularities of certain samples. And with all these advantages, if you don't obtain insightful conclusions or an improvement, why are you using it?
Good question, yeah. Well, another reason why maybe not to use it is, as you say, it's a black box, whereas other models are a bit more interpretable. Random forest in particular has a method where you can score each feature for its feature importance and giving you some indication of how the model's working. Can you speak at all to feature importance for the models you're familiar with? When you're getting up very close to 100% accuracy, what is the model looking at to be so wise about the future?
In our work, we present an extensive benchmark with shallow models and also, of course, deep learning models. But the one that is most important, at least to me, is what we call the latest value. The latest value model, it is a naive model where the traffic value that is predicted is actually the latest one that was seen by the model. So, for example, if samples of the time series, the traffic time series, are coming in a frequency of 15 minutes, let's say, the latest value model is going to predict for the next time stamp the latest value that has seen. And only with this naive model, we can achieve a high accuracy, an 80% accuracy in some cases, an 80% with the latest value, without processing.
This seems very surprising. Is some of it due to the fact that traffic doesn't change much during boring parts of the day, so it's easy to predict?
Yeah, that's the point. The traffic time series do not change too much between following samples. So if you already has access to the latest traffic record, you have more than half of the task already done. Of course, if you use the information of the last hour, you can predict better. So I would recommend to use a random forest, for example. But if you use a complex deep learning with a ton of internal layers, you're not going to excel that performance. So there is no point to use it.
Thanks to this week's sponsor, Masterclass. With Masterclass, you can learn from the world's best minds, anytime, anywhere, and at your own pace. You can learn about the science of better sleep with Matthew Walker, learn music for film from Danny Elfman, or learn conservation from Dr. Jane Goodall. With over 100 classes from a range of world-class instructors, that thing you've always wanted to do is closer than you think. I just started that Danny Elfman course. It's really good. I'm a big Oingo Boingo fan. I knew he did films, but I didn't know the depth of thought that was there. These master classes, they're really productions. I might be able to get Linda to watch one with me. They're well worth your time to check out. This holiday, give one annual membership and get one free. Go to masterclass.com/dataskeptic today. That's masterclass.com/dataskeptic. Terms apply. If you have ever wanted to make your home feel safer, there's no better time than now. This week, our friends at SimpliSafe are giving Data Skeptic listeners early access to their holiday deals. 40% off their award-winning home security. We love SimpliSafe because it has everything you need to make your home feel safe. Indoor and outdoor cameras, comprehensive sensors, all monitored around the clock by trained professionals who send help the instant you need it. SimpliSafe was even named Best Home Security System of 2021 by U.S. News & World Report. You can easily customize a system for your home online in minutes and get free custom recommendations from SimpliSafe. Now remember, these are SimpliSafe's biggest discounts of the year. Now's the time to act. You gotta get a complete home security system starting at just over $100. There's no long-term contracts or commitments. It's a really easy way to start feeling a bit more peace of mind. Take advantage of SimpliSafe's holiday deals and get 40% off your new home security system by visiting simplisafe.com/dataskeptic. SIMPLISAFE, simplisafe.com/dataskeptic for 40% off your entire system. What about if traffic is kind of behaving the way we intend it to or the city planners do, it should be very predictable. But of course, the time when I most need the forecast is when it's in an unpredictable or unusual state. Could it be that those, very important rare cases are what's in the last bit of accuracy that models aren't achieving?
Yeah, exactly. We are not going to hit never the 100%. It is impossible because the traffic behavior as a natural task, it is very, very, very complex. You have a lot of factors, including if you are inside a city, the traffic lights, if people is suddenly stopping, if there is an accident that sometimes occur. So with all these events that are not predictable at all, well, you can narrow and make predictions with confidence factor, but you cannot tell 100% that is going to happen. You can never tell 100% if there is going to be a congestion. But for example, we all know if we go every day to work at 7 o'clock in the morning and every Monday we have a congestion, well, the next Monday, if you need to bet, you're going to say Monday of congestion.
Well, if I were to study individual, let's say, intersections, or even, the ones that I drive through every day, I've come to learn them. I have some understanding of if they're usual or unusual, if maybe, the nearby stadium could affect things. I feel like I'm bringing a lot of my human intelligence to the table. Are there ways that context can be modeled in the prediction as well? Could there be a benefit by recognizing the type of an intersection or something like that?
Yeah, of course, there are a lot of publications concerning this topic, but for the paper that we are talking, we mainly focused on short-term forecasting. And as I said, for short-term, you only need the past traffic behavior, the 1 hour in the past. But for long-term, when you try to model the traffic behavior, for example, we have another publication when we cluster days, if they are a normal work day, if they are a holiday weekday, then it is interesting to see if the road is near to traffic stadium and if there is a match on that date.
And can you talk a little bit about the results?
What we tell in that paper, in that publication, is that If you have access to enough information just to characterize well the traffic behavior, the traffic profile, as we call it, do not need too much any kind of modeling, predictive modeling technique, because just using the traffic profile, which is the mean of all the samples that falls inside a cluster at the A type, what are you going to obtain is an error so low that it doesn't even matter to use more complex modeling techniques.
If I were to be a cynic of this work, maybe I would say you just didn't tune the model or you didn't use the right architecture. Had you done so, there would have been some breakthrough in deep learning and shown that it's necessary here to get some extra amount of precision. Do you have any thoughts on that, kind of untestable claim?
Yeah, in the paper, first of all, we provide access to all the code for the simulation, so everyone can see how we have done the benchmark. And we also use an hyperparameter automatic tuning tool. So every single model, I don't mind if it's deep learning based or shallow learning based, is optimized in the same way.
And one of the things you mentioned in the paper is the use of those hyperparameters, that sometimes that's a neglected feature, and maybe if people, I guess this is my inference, but if people paid a little bit more attention to their hyperparameters, they might find simpler methods working as good or better than the heavy-duty deep learning approach without the cost of compute and all of those things. Is that accurate in what you guys found?
Yeah, of course. What we found is that if you must use deep learning technique, because this task is so easy to achieve, you don't need to stack a ton of neural networks and each neural network to have 1,000 neurons. Maybe with 10 neurons it is enough. And because it is the complexity of the neural networks grow exponentially with the number of layers and with the number of parameters each layer have, what we are trying to say is that you don't have to complicate yourself too much. A few layers, let's say 3 neural layers with 10, 100 maybe, it is enough, because we tried with 1,000 of neurons per layer and deeper architectures, and the results are not better. If you go to figure 5, we can see that the results, the performance, feed-forward neural network, convolutional and LSTM based, and also an attention-based, which is, for me, too complicated, too deep, and they all output the same performance. Why? Because there are not more complicated relationships to model. It is the end of the road. There is no more. So you don't have to push it further.
So if it's the case that a short-term forecast is really almost entirely explained by the last hour's worth of data, then that would imply there aren't too many external factors. Is that a fair take on it?
I would say not too much. The thing is that a paper that focuses on short-term forecasting, it is going to be published. So it is a mean for fast publication. With that idea in mind, everything is bad. So what I would recommend for people that is interested in traffic forecasting is to let this aside and to focus more on traffic profiling or into graph neural networks that I would like to talk about, because this kind of graph-based neural networks are interesting because what are they trying to do is to model the traffic network with graph theory and then to input this graph and all the traffic metrics into the deep learning model. And with this, to obtain a full network forecast. And that's interesting.
So if we don't need the deep learning techniques for short term, what's changed when we zoom out and look at the large global system? Why does it become an appropriate methodology there?
Firstly, the short-term forecasting models, they only forecast for one street. So if you need to forecast 10 streets or 100 streets, you need 100 models, and each model to be trained with target data. But with graph neural networks, you are able to predict all the traffic state in a vast area, let's say a city, for example, with just one model, and also to learn the relationships and traffic correlations between distinct road segments. So you are improving your modeling performance because the model is seeing all data from all the city.
Well, that's a much harder forecast to make, I assume. Can you speak a little bit to the state of the art? How good do people do, and what are the algorithms that seem to be succeeding?
Well, just a little bit because I do not deep too much with this technology, but mainly what you are trying to do is to make non-Euclidean representation of the map. Then if crossroads are the nodes of a graph and the edges of the graph are the road segments, where you try to input in each segment the traffic time series from your dataset, and you just feed to the deep learning model. You need to have the knowledge to make these inputs work, but then it's just a matter of turning parameters and train properly the network. And then what are you going to obtain is a set of predictions which are labeled for every location of the network where you have access to data.
When you think about rolling out a system like that, I see a number of challenges. One is the scale. If you want to do something for like a whole city, the data must be enormous. The data pipeline you need to process it has to be built. But even within that, I'm sure as the data set gets wider, you're dealing with more issues of, maybe a solenoid is out or down, or just a lot of outliers and things show up in the data. Where are the places where the most effort has to be put in? What are the current state struggles for projects like that?
Mainly data preprocessing, without a doubt, because as you said, you need a vast amount of traffic data. What everyone desires is to have data at every location of a city or a freeway map. But because you don't have it, you have to work with the data that it is available. So you are not allowed to have a lot of errors on your data. You have to clean it so well. And if everything is already clean, you just need to pick the model you like and to make a fit predict. It is that easy.
And we've mentioned, I guess, the solenoid technology. I think you'd also describe the possibility of, I don't remember what term you used, but I guess our cell phones are all measurement devices if we opt into some service. That's got to be a data set with its own forms of outliers and challenges. Have you spent much time looking at GPS tracking?
No, I don't work with that kind of data, but the problem with that data is that mainly the datasets that are available are from bike data or from taxi data. So because you only have access to an exclusive vehicle type, you cannot model traffic flow. You can only model the trips, the paths that they follow, and also the main speeds of the road if you average them according to the floating car data. So I don't like too much this kind of data. It usually have a mediocre data quality in the form that the GPS has its own positioning errors. The accuracy is between 3 meters. So it is interesting for some kind of investigations, but for traffic forecasting, it is not the highest data quality possible.
Well, before I go into a wrap-up, I usually like to ask, is there anything I didn't ask about that you think we should have covered?
I would like to say that we are also working with another kind of modeling techniques, which are called randomized-based models. And what we prove is that these kind of models that are based on the idea that you just set a set of random weights on a neuron layer, and then you let the model to learn the relationships and the connections that are interesting for the task itself. So I would recommend to read about random vector functional link machines, eco-state networks, and also extreme learning machines. Because, for example, for this kind of task where it is the performance gap is narrow and you don't need very deep model, what you are going to achieve is a low resource demanding model and fast training times. And in the case that you need 1,000 models, which each model is going to learn and predict for just one location, randomized-based techniques are interesting, without a doubt.
Is that the next direction for your research, or are there other things you're looking at as you move forward?
Maybe not the main direction, but we like to sometimes publish and investigate research a little bit with that kind of modeling. But as we are saying here, the problem with traffic modeling is not on the modeling techniques. It's more forward the data quality and the data profiling techniques. So actually we're trying to, just from seeing a traffic map, we're trying to select which traffic segment is closer in the form of the traffic profile to another one. So imagine that you have access to traffic data only at several roads of your city. But you hardly wish to have data at another location, but you don't have the resources or the time to put a traffic sensor. If you are able, just from seeing the traffic map, from topological features, to guess from your available set of datasets from where to extract data, I think it is interesting because you can boost your model performance, you can boost the number of the forecasting area that you can actually cover. And yeah, in a nutshell, if you see a traffic map, to foresee or to guess the relationships between two roads that do not need to be geographically close between each other.
Well, if data quality is a concern and you don't have full coverage, is there any opportunity that cameras could be of some use in generating more data? They've become quite ubiquitous and relatively cheap these days.
Yeah, of course, but it is more expensive after all because you need to record a video which occupies more memory, and then you need to process with a nice algorithm, a nice computer vision algorithm that is going to have some misleading errors. And why to use this if you already have the access to the technology of inductive sensors or infrared radars? But yeah, I've got your point that cameras are already installed, but maybe it is a good idea.
Where can people follow you online?
They can follow me on LinkedIn and also at ResearchGate.
I'll have a link to more of your research in the show notes for people who want to follow up. And thanks so much for taking the time to come on the show and share your expertise.
It's been an honor.
That concludes another installment of Data Skeptic Time Series. Our guest today, Eric Manibardo. Thanks to our sponsors, Masterclass and SimpliSave. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, and our host, Kyle Polich.